And the computer, hold on. Am I projecting? Oh, I see. Good, okay. Right. I've never been in a room with so many friends, and therefore I'm going to begin by taking a picture. Okay, smile. Thank you. It's really amazing, unbelievable. This is going to be a bit unusual. It's a mode of presentation I haven't tried before, totally tied to this document. So everybody needs a copy. There are a few around. If you don't have one, raise your hand. Who doesn't have one? So would you, if you see extras, would you pass them back? You need this. It is online, and if you're going to play with it yourself, you need the online version because that enables you to copy and paste, and that's what I'm going to do. This is much too much material to present at a pedagogical rate, so I've decided to abandon the pedagogical rate and rather show you a lot of cool stuff a little bit too fast. However, there is some information there in the handout so you can learn more with references, and you can execute things all yourself. Chebfun is part of the discussion. A lot of it's just MATLAB, but so MATLAB and Chebfun, you can get everything about Chebfun there. You need a pretty recent version for some of the things that I am doing, though not all of them. So as I say, I've never tried this mode before, and we'll see how it works. Now, raise your hand if you don't have a copy. I see a few still. Can we pass these back? Percy. If you look at the document, oh, you must keep it for tomorrow and Wednesday. It's the same thing, and I don't have any more. You'll see that today and tomorrow are written out reasonably in full, and then I ran out of time, of course, and the third day is not written out. Luckily, I also ran out of time to overwhelm you quite as much, even on the first 2 days, as I intended to. So you'll see on the table of contents some things in square brackets that we won't talk about. I won't talk about Hankel contours, where Andre Weidemann is the great expert, or steepest descent. Yuji Nakatsukasa is speaking about section 2.2 tomorrow, Vandermonde with Arnoldi. I won't speak about numerical uses of conformal maps. Okay, so let's get going. So we begin with contour integrals. We're talking about numerics, of course, and the way these notes are constructed, everything is a numbered section. I decided to act French for the purposes of this lecture. And in every section almost, you'll find a demonstration in MATLAB or Chebfun illustrating the concept we're talking about. So let's begin with the fact that if you have a power series, an analytic function, it's obvious from the power series that the value at the middle of a circle is the mean of the values on the circle. So to demonstrate that, we've taken here e to the z, and if I copy and paste that bit of code into there, we're taking the mean over 18 points on the unit circle to find e to the 0. So there's e to the 0 approximated from 18 points, 18 roots of unity. Now, of course, there are many ways to do integrals. You could use software, for example. So in Chebfun, you could construct that function e to the iz on the unit circle. You could make it even periodic if you wanted with the trig flag. So here we've constructed that function as a periodic function, and then we've called the Chebfun command mean, and it actually gets it exactly. Of course, you could call a MATLAB code if you still do quadrature in the 20th century fashion. So there's the integral command from MATLAB, which will also get the right answer. There you are. So the mean value is the most elementary concept of complex analysis, but of course that's essentially the same as a Cauchy integral. You just make the observation that the absolute value of the differential is related to the complex variant. So here we'll do the same thing as a Cauchy integral, and just for fun, instead of integrating over the circle, now that we have a Cauchy integral, we can deform the contour. Let's integrate over a square. So here in Chebfun, we're making a square with 4 sides, and the join command is used to make that square. And if I execute that, I should again get the same answer. Yes, of course it can be non-square. And there are examples at the Chebfun example site of all sorts of contour integrals, keyholes, and things like that. Now, first application of of contour integrals is this wonderful way you can use them to evaluate functions near points where they are troublesome because of a removable singularity. Everybody's favorite example of that is one of these phi functions, like e to the z minus 1 minus z divided by z squared. That's an entire function, but if you try to evaluate it from the formula at near 0, you're in trouble. So, for example, here, suppose we, where are we here? What I'm going to do here is first evaluate it from the formula at 10 to the minus 5th and 10 to the minus 10th, and then use the mean over the unit circle. So look here, if you at 10 to the minus 5th, you get about 6 digits of accuracy. At 10 to the minus 10th, you get nonsense. And of course, there's a problem cancellation in floating point arithmetic. But using the mean over the unit circle, you can do wonderful things. And this is a trick that people have used to great effect. For example, there's an amazing paper by Bengt Fornberg and Grady Wright in which they use this trick to do fancy things with radial basis functions. Now, when you take sample points at roots of unity, this is a version of the trapezoidal rule, and it's the very best version of the trapezoidal rule, a periodic integrand that's analytic and equally spaced points. So no demonstration here, but the history is interesting. It was Poisson in the 1820s who first noticed that the trapezoidal rule had this magical fast convergence in certain circumstances. It wasn't proved until Phil Davis in 1959, but he describes it as folklore. Everybody knew this. They just hadn't written down a proof. Now, getting into derivatives. Suppose you want to know the case derivative of an analytic function at the origin. Well, you could plug the case derivative into your same formula, and there's an equation for it. If you then integrate by parts k times, you get the usual Cauchy integral expression for the case derivative of a function, or equivalently, the case Taylor coefficient. So let's do that. Let's evaluate the fourth derivative of the square root of 2 minus z by taking means over 40 points. So here we have the square root of 2 minus z, and I take the mean, and so this is the exact answer. 40 points gave us full precision. I'm going to attempt to adjust this window ever so slightly, hoping that makes it a little more visible in the back. Any comments on visibility? Raise your hand if you'd prefer a larger font. Okay, I guess that's not enough. You can move forward. Now, once you're getting Taylor coefficients by taking means over roots of unity, you're essentially doing the discrete Fourier transform, and you can get them all at once, not just one at a time, by using the FFT. So that's an O of n log n algorithm for getting all of these approximate Taylor coefficients. So for example, here's e to the z. Let's take just 18 roots of unity and use them to compute Taylor coefficients. And you can recognize that, well, at least you can recognize the first few are accurate to machine precision with, what did I take? 18 points. So a little bit of history here. One of my heroes is Carl Runge, and he has a book in 1904 about series, which is amazingly computational in orientation, though, of course, long before computers. After computers were invented, one of the people who started pushing complex variables was Linus, who died a few years ago, James Linus. And he wrote papers with a bunch of people, including Cleve Moeller, advocating complex variables. I like this quote from Linus and Moeller. Once complex arguments are allowed, the principal difficulties encountered in numerical differentiation simply disappear. And that's what we saw, not yet with differentiation so much, but with evaluating that phi function with the removable singularity. The early papers didn't use the FFT, even though they probably were aware of it, but pretty soon people noticed the FFT connection. And when I was a graduate student, Peter Henrizi wrote his survey paper in Siam Review about fast Fourier methods in complex analysis. Now, what about accuracy of these things? Well, you know, one of my principles in life is that complex variables is easy and real variables is hard. Because real variables is always at the edge of smoothness. You're trying to do fine analysis of things. But in complex variables, the basic fact is always easy. And the basic fact is something is converging geometrically. So long as you're in a region where a function is analytic, power series work, everything should be easy. So here's an example. If you have an analytic function that's analytic in a neighborhood of the unit disk, let's say in a disk of radius capital R, then you can deform the contour to get an estimate of the Taylor coefficients. And this is called Cauchy's estimate. So the Taylor coefficients of an analytic function decrease geometrically at a rate determined by that radius. I think there's a lowercase r. That should be an uppercase, shouldn't it? Capital R to the minus k. From that, you can quickly figure out how accurate these discretizations in roots of unity are because of aliasing. So the principle is that a power z to the k is indistinguishable from an alias of that power with a lower value of k between 0 and n. So if you follow through that reasoning, you quickly find that the discretization error in the 0th Chebyshev Taylor coefficient is O of r to the minus n. The rounding error is O of 1, or I should say O of machine epsilon, for comparison. But now you start saying, what if I adjust the radius of the circle on which I'm sampling? Closer in should do better. And sure enough, that's true. Follow through the same reasoning. You find that if you sample on a circle of radius little r, and your function is analytic in a circle of radius big R, then your discretization error in the kth Chebyshev coefficient should look like little r over big R to the n plus k. So geometric convergence, and the smaller the radius, the better. Now, the trouble is, when you take things to a smaller radius, you also get a little r to the minus k when you look at the rounding error terms. Because what you're computing as a linear combination of bigger and bigger numbers. So on a computer, even though mathematically that linear combination may be great, it may be awful on the computer because of rounding errors. So you have an interesting problem. Discretization error says we'd like the sample radius to be small. Rounding error says we'd like the sample radius to be large, at least when computing higher derivatives. Bengt-Fornberg wrote a paper back in '81, adaptively adjusting the radius to try to get things optimal. But the full analysis is by Volkmar-Bornemann. Where are you, Volkmar? An amazing paper by Volkmar in which he really beautifully shows a very general picture about this choice of radius phenomenon, which I'm not going into the details at all. But anyway, here I've modified one of the codes to explore different radii. So we're now trying to compute a fourth derivative, and I've scaled things so that the fourth derivative we're trying to compute is 1. So I have an input command here. Let's do that a little higher up. Okay, so when I run this thing, it asks me to specify a sample radius. Where am I going to sample my points? If I try 1, then you can see I'm getting 4 digits of accuracy. If I try a half, I get 6 digits of accuracy. If I try a quarter, I get 8 digits. If I try an eighth, I get 10 or 11 digits. If I try a 16th, I'm beginning to lose accuracy now because of the rounding errors. If I try a 32nd, if I try a 64th, so we're losing more and more digits. I'll try 129th. Who knows what 64 times 2 is? Uh, see that sequence, 8, 16, 32, 64, 129? When preparing this talk, I encountered the annoying fact that for some reason of coincidence. Okay. What's that?
That does look like an annoying.
It was very annoying. I thought it's funny when you think you've made an error and your results are coming out accurately. I must have made an error. So. Yes, yes, if you believe in that. It's amazing how the symmetry gets lost, isn't it? Yeah. So one way that Taylor series arise is in generating functions. And in fact, if you're Don Knuth, this is the most beautiful thing about Taylor series. And if you want to read, this example is the Bernoulli numbers, and the Knuth's book has an amazing discussion of that. So here, it turns out that the Bernoulli numbers are coefficients suitably adjusted of z over e to the z minus 1, Taylor coefficients. So let's, if you run that code, you see we're just sampling in 80 points, 80 roots of unity, and we're getting full precision. Except we're not using roots of unity, we're using a sample radius of 4, because this is a typical application where, following Folkmar's theory, if you use a sample radius of 1, it's very far from optimal, whereas 4 is a pretty good compromise. You know, I'm always interested in historical asides, and one of our favorite, it's a footnote in the paper by me and Andre Wedemann about the trapezoidal rule, is this idea of complex step differentiation and how it fits into this picture. So going back years, and certainly to a paper by Squire and Trapp, is this cute observation that you can sort of do automatic differentiation without doing automatic differentiation. If you want the derivative of a real function, just step into the complex plane some microscopic distance and do a finite difference, and you get full precision. That works. The conventional answer would be that it works because the real and imaginary parts of a number are independent, so they're each scaled relative to something. So here we're taking a finite difference to compute the derivative of e to the x at 0, taking a finite difference with step size 10 to the minus 100, and it works. But you can also regard this as an example of the trapezoidal rule, or of roots of unity. We only have 2 roots of unity, but that's enough if the radius is sufficiently small and rounding error isn't a problem. So there you have the derivative of e to the x at 0. Now, another aspect of this clever manipulation of radii, which Folkmar emphasizes in his paper, is that you can compute Taylor coefficients below the level where you would think you would be able to. So obviously we can get them down to 10 to the minus 16th, but you can go further if you take a larger circle on which to sample your function. So here we're trying to compute the, 30th derivative of e to the z at the origin. And you see the exact result is 3.7 times 10 to the minus 33, and sure enough, we get 3.7 times 10 to the minus 33. You'd never get that by sampling on the unit circle, but you can get it by sampling on the circle of radius 12. Now, of course, you can't use that to ultimately compute anything to more than 16 digits of accuracy, but you can use it to compute things involving higher derivatives to close to 16 digits of accuracy, which you'd never do by sampling on the unit circle. Okay, so now we come to a big conceptual thing. This first part of the talk is closely tied to a paper by me and Peter Cravagna and Anthony Austin, published 2 or 3 years ago in the Siam Journal of Numerical Analysis. And one of our themes there is the relationship between contour integrals and polynomial interpolation. So imagine you have data at roots of unity and you want to evaluate your function. One way is with a Cauchy integral. Another way is simply interpolate by a polynomial and evaluate the interpolant. Now, that second idea is strangely not so famous. And I think the reason it's not so famous is that if you're evaluating at the center point, they turn out to be the same. So that's what Linus and his friends were doing, mostly evaluating at center points. So if they ever thought about polynomial interpolation, they didn't need to use it. So here's an example. But now, if you're not evaluating at the center point, it really does matter whether you're doing this or not. So here, I'm evaluating e to the 0.9 and getting full precision by interpolating by a polynomial in 20 points and evaluating the interpolant. Here's another way to do the same thing with the barycentric formula. So as we all know, the beautiful way to do polynomial interpolation is a barycentric formula. Here's the barycentric formula for roots of unity. You see, again, we get full precision. Now, this differs from using the Cauchy integral. So if you do the Cauchy integral, it turns out that boils down to this: catastrophically inaccurate. So we've only got 1 digit of accuracy with the Cauchy integral and 16 digits with polynomial interpolation. They're very different algorithms, as long as you're not evaluating at the center point. Isn't that interesting? And of course, there is some history of that. And the people doing fancy integral equations use tricks like this. Somewhere or other I mentioned QBX, which is quadrature by expansion. And that's related to this use of series. But now I want to emphasize this curious phenomenon. You see, that formula is the quotient of 2 means. And that was for barycentric polynomial interpolation. This formula is just a single mean, the numerator of the other one, for Cauchy integrals. So we have this weirdly similar formulas. And what happens is that when you do barycentric formulas, you're taking a perfectly reasonable expression and then dividing it by an approximation to 1. And the wonder of barycentric formulas is that that division by 1 improves your answer enormously because the errors cancel out to leading orders. So a few people over the years have noticed that. And one is Iachimidis, who's written several papers 20 years ago about this distinction. If you look at the accuracy and get a theorem about that, you find that the error, if you do polynomial interpolation, is essentially independent of where you're evaluating your interpolant. Whereas if you do it by Cauchy integrals, you have capital R to the minus n, that's the good small term, but then it's worse. It's the maximum of that and the evaluation point to the n. So when you're near the circle, you lose your accuracy with Cauchy integrals. Okay, let's move on. What about Laurent series? So far we've been in the unit disk, analytic in a disk, but suppose you're analytic on the circle or in a neighborhood of the circle, an annulus. Well, then, of course, we have Laurent series. So there they are, the same formula, but now with negative as well as positive powers. So here's a code, for example, in which we use 150 roots of unity and the discrete Fourier transform, the FFT, to evaluate Laurent coefficients of square root of 1.3 minus z over z to the minus 0.5. So if you think about that, the closest singularity outside the disk is at 1.3. The closest singularity inside the circle is at 0.5, which is a bit further away. So if I now execute that, here's what I find. This is a picture of the amplitudes of the numerically computed 150 Laurent coefficients. You can see on the left we're dominated by the analytic part of the problem, that singularity at 1.3. On the right, we're dominated by the co-analytic part of the problem, the singularity at 0.5. Notice that curve is steeper than that curve because 0.5 is further from the circle than 1.3. Notice also that eventually they meet in the middle, and there are also aliases of these things in all possible directions. So in some sense, they're both going on and then being added up. Now, one thing about the circle and annually is that that's very close to Chebyshev methods, because as soon as you take the Joukowsky map applied to that, you get Chebyshev. So for example, I'm skipping all the math here, but this is one of those rare rooms in which people know the math. Here I'm going to compute Chebyshev coefficients, but using the FFT. So what's happening here is we have e to the x, and I'm sampling at 32 roots of unity, and I'm explicitly transplanting e to the x to the unit circle and then using the FFT. Normally you wouldn't do this, you wouldn't use complex arithmetic if you could avoid it, but here you see we are doing that explicitly. So we will now compare Chebyshev coefficients against their exact results, which are Bessel function evaluants, and you can see 32 points gives beautiful accuracy in these Chebyshev coefficients. Now, of course, Chebfun is all about Chebyshev series, and I'm trying resolutely not to talk about Chebfun in general, but always to keep the focus on the complex plane. Once I get into in general, I'll never stop. But anyway, here, for example, suppose I just want to compute the Chebyshev coefficients of e to the x in Chebfun. Well, I could say plot coefs of that, and there you see decreasing down to machine precision, and it's cut off automatically at machine precision. So those are the Chebyshev coefficients of e to the x. They're decreasing faster than geometrically because e to the x is not just analytic, it's entire. Oh, and the most fun here. So there's a turbo mode in Chebfun, which uses the Bornemann trick, but now we're in Chebyshev land, so it should be called the Huybrechts and Wang trick, because they did what Bornemann did on the unit disk, Huybrechts and Wang did for Chebyshev. Chebfun has a thing we call turbo mode, which enables you to evaluate Chebyshev coefficients, not on the interval in the usual way, but on an ellipse further out. So if I run that, sorry, I closed this, something I shouldn't have closed. Let me run first the first one again. And now let me run the second one. So you see, standard Chebfun would go down to machine precision, but in turbo mode, you get further, and obviously it's not perfect, it's some crude adaptive idea, but you really do genuinely get real information about further down Chebyshev coefficients. Now, what about matrices? In computational science, a lot of the excitement about complex variables is applications to matrix problems where the matrices are very big. And if there's one theme in this excitement, it would be that with complex variables, you can reduce things to backslash. You can reduce complicated problems to solving AX equals B, which for various methods we can often do efficiently. So here, for example, I'm computing the cube root of a matrix. It's just a 4x4 matrix by doing a Cauchy integral. So you can see the error in my cube root is exponentially diminishing. By the time I have 64 sample points, I have error machine precision. Okay, so effectively, I'm through the first half of what I wanted to show you. We're on schedule. Any questions, comments? Okay. So what we've done so far is basically to evaluate functions. Scalars mostly, but it also works for matrices. Now we want to evaluate zeros and poles of functions, and once you have a matrix, that becomes the problem of finding eigenvalues. So there's, of course, lots of history here, and just to make a comment about history, the easiest way to find the roots of a function in the unit disk is to interpolate by a polynomial in roots of unity and then find the roots of that interpolant. Now, nobody seems to have suggested that idea until 2014, when we did it and also John Boyd in his book did it. It's remarkable. Maybe it's out there somewhere, but I don't know where. Although Jack Good proposed the Chebyshev version of that idea in 1961. So this is what Boyd calls proxy root finding. You approximate a function by a polynomial, find the roots of the polynomial. So here's an example where we want to find the roots of cosine 2 pi z in the unit disk. So we find the Taylor coefficients, and then we use the MATLAB roots command to find the roots of that polynomial interpolant in the unit disk. And the exact roots are plus or minus a quarter and plus or minus 3/4, so you can see it works very nicely. Now what we just did I would call roots from coefficients, where we've taken Taylor coefficients and used them to do something. But there's always a dual. Anything you can do with coefficients you can do by values. And if you want to find roots of something by values, there is this dual approach involving a generalized eigenvalue problem. Now, Rob Corliss is the guy who taught me about this stuff. I don't know who first did it, but you're certainly the first who did a lot of these things. So roots by values instead of roots by coefficients. And I guess number 10 is a paper of yours, but we don't seem to yet have the great reference on this subject. Somebody needs to write the great paper. This particular version was developed for me by Alex Townsend. Well, not for me, given to me by Alex Townsend.
I think I got it from Piers Lawrence.
Well, you got it from Piers, who worked with Rob, right? And where is Piers now? He was at Leuven, but...
Proud father.
He's what?
He's a proud father.
He's a proud father. Okay, good. So now we've done, in principle, exactly the same thing by values instead of coefficients. But as you might imagine, well, as I just said, there's no tradition of doing this. No tradition of interpolate by a polynomial, find the roots of the polynomial. No. The tradition is contour integrals. And that, of course, going back to the 19th century, Cauchy knew formulas for relating roots to contour integrals. So in the 60s, people started proposing such things. There's a paper by McCune, and then a more influential paper, perhaps, by Delves and Linus, in which they recommend an integral involving f prime. Now, to keep things simple, I'm going to avoid f prime and just use values of f itself. So there's a variant on that called by Luck and Stevens, which is this integral here. Notice it looks just like a barycentric formula. It's amazing. All these things are so intertwined. It's one integral divided by another, which is sort of like 1. So here we have an implementation of that idea. So now it's a truly different approach. Now it's contour integrals rather than interpolation. And that doesn't look right, does it? Oh, I'm sorry. Yes, it is right. I wasn't thinking. Sorry. When you do polynomial interpolation, the very base concept gives you all the roots in the disk. Once you have contour integrals, you have to think more. How many roots are there in the disk? And this implementation is just to find a single root in the disk. My function is log of 1.1 minus z, which has a single root at 0.1, and you can see it has found it to full precision. But now what if you have more than one root that you're trying to find? And let's suppose you know a priori that you have capital K roots. Well, it turns out there is a generalization of this idea, and it was developed by Cravagna and Van Barrel, who wrote a book, and it beautifully involves a pair of Hankel matrices and a generalized eigenvalue problem constructed from these Hankel matrices. Really cool stuff. So there, if I run that, 180 points now, generalized eigenvalues. The Hankel matrices are only of size capital K. They're not of size 180. So it's a very efficient method. And there you can see we've computed these 4 roots in the unit disk of my cosine function. Now, what if you don't know how many roots there are in the disk, but at least you know it's analytic? Well, then, of course, you can use the argument principle, and there are many flavors of that. For example, I could evaluate an integral, and here I'm evaluating an integral which tells me there are 4 zeros of my function in the unit disk. But somehow it's a little annoying to use an integral because the basic concept is even more elementary. There's a thing called unwrap, which Nick Hyam and his students have done fancy generalizations of. Stefan, remind me who the student is. Was it Mary? Who worked on the It was Mary, right, okay. I didn't remember which. So Mary Abrahamian wrote a thesis related to fancy versions of unwrapping things. This is a very simple scalar version, and the point is that if you take a function that's going to cross branch cuts, you can connect the dots in a fruitful way and avoid those jumps by 2 pi with unwrap. So this function changes by 8 pi over the circle. So at the top it's computed there are 4 zeros of this function. That was with Chebfun unwrap, but you could do the same thing with just MATLAB unwrap. The final result you care about is known to be an integer, so you don't need great precision. So there's a discrete analog. Again, reaching the conclusion that this function has 4 zeros in the disk. Now, what about pole finding? Well, in a sense, zero finding and pole finding are the same, just take the reciprocal. But that's not really true, because it's reasonable to assume you know you have a function with no poles, but it's not reasonable to assume you have a function with no zeros. So you can't quite just take the reciprocal and use your zero finding methods. However, some methods do work, and here's one. Suppose you take data in roots of unity, interpolate the data by a rational function, and then find the roots of the denominator. An obvious way to estimate poles of a function. In particular, suppose you do that interpolation in a linearized fashion. So you're not actually interpolating f by p over q, but you linearize to make it nice, robust linear mathematics. So fq minus p, you do some mathematics on that. You could even make it a rectangular matrix and it becomes least squares. If you do all that, this is the interpolation style way of getting roots. Approximate by a rational function, find the roots, the poles of that rational function. And here let's do that for the tangent of pi z. So the tangent of pi z has roots at plus a half, has poles at plus a half and minus a half. So if I run that, I find, sure enough, we've got about half precision. I only took 40 points rather than 60, so I only have 6 or 7 digits of accuracy. Now, this is not a standard idea. Nobody did that till our paper a few years ago. But a somewhat more standard idea, although still not so well known, I guess, would go back to Krivania and Van Barrel again, where it turns out that if you do the same thing with the generalized eigenvalue problem involving the Hankel matrices, you can estimate poles in the unit disk. So let's do that. So we've now used this completely different method and got good results. And you notice it's the same. The errors are the same. And that's no coincidence. It turns out these different methods are equivalent. So the Krivania-Van Barrel method by coefficients is equivalent to this linearized rational interpolation method by values. They're mathematically identical, although numerically different. Okay, well, the last real topic is, what if we have eigenvalues of a matrix that we want to find? So, of course, eigenvalues are like poles in some sense. They're poles of the resolvent. So if we wrote the resolvent formula right there, if we wanted to compute poles of it, we could scalarize it by multiplying the resolvent matrix by a column vector on the right and a row vector on the left, maybe random vectors, or who knows. So here we've done that. We've taken the resolvent and multiplied it by random vectors on the right and the left. That gives us a scalar function with poles at the eigenvalues, or at least with probability 1, there will be poles at the eigenvalues. This particular matrix is a 4 by 4 matrix, which happens to have been constructed to have eigenvalues at 0.2 and 0.3. So when we do all this stuff with the generalized eigenvalue problem with the Hankel matrices, we hope to find the numbers 0.2 and 0.3. So, well, we succeeded. We got 0.2 and 0.3. So that's pretty cool. Now, there's a lot going on. Whenever you do a resolvent integral, there's a lot of interesting mathematics. And I hope you all know the book by Cato, This is a thick, impenetrable-looking Springer book. It's about 6,000 pages long with a blank yellow cover. If you don't know it, you'd be terrified, but it's a great book. It's really wonderful. And you only read half a page at a time, but it's always exactly perfect. So to learn about this stuff, Cato is your place. One thing we can find in Cato, as in many other places, is that the idea of using contour integrals to project things onto invariant subspaces. So in particular, suppose you do a contour integral to evaluate f of a, but f is the function 1. Then you should get the identity matrix. But suppose your contour doesn't enclose all the eigenvalues, just some of them. Then instead of the identity matrix, you get the projector onto an invariant subspace associated with the eigenvalues inside the curve. So that's a beautiful mathematical idea, which turns out to be more important than you might imagine in computational science. So here we're doing it for this example, which is just a 4x4 matrix. I'm explicitly adding up at n roots of unity the appropriate thing to approximate that integral. So I should get the projector onto the invariant subspace associated with eigenvalues 0.2 and 0.3. So I run that. So this is a projector, and the output I'm going to produce is the eigenvalues. So if you think about it, I've projected from a 4-dimensional space to a 2-dimensional space. So the eigenvalues should be 1 and 1 and 0 and 0. And sure enough, there they are. Now, at first, I was actually computing singular values, and was surprised till I thought about it, because they're not 1 and 1 and 0 and 0. They're 8 and 2 and 0 and 0. Because in general, projectors are not orthogonal projectors. They're just projectors. So in the course of projecting onto this 2-dimensional subspace, you can actually enlarge things, in effect. So now we get into the part of this lecture that's closest to what people really care about in computational science. Use of these projection-type ideas for large-scale eigenvalue calculations. And in order to show you what I want to show you on that, the key thing is to look at contour integrals not just as contour integrals, but as projectors. And when you discretize them, you're approximating a projector. It turns out if you discretize the identity projector in n points, you're effectively multiplying your function by that thing b of z. So that's a very interesting function, b of z. Let's just talk about b of z for a moment. That's not working. Oh, well. That function b of z, when z is inside the unit circle, that function is approximately 1. And when z is outside, it's approximately 0. So this is a filter that essentially annihilates things outside the circle and leaves unchanged things inside the circle. And in fact, it's related to the Butterworth filter of electrical engineering. If anyone knows the Butterworth filter, it's exactly this, but with just a semicircle instead of a full circle of poles. Now, it turns out when I do my discretized Cauchy integral, what I'm doing is multiplying each eigencomponent of a vector associated with eigenvalue z by that number. So the eigencomponents outside the disk are being attenuated, and the eigenvalues inside components are being left more or less unchanged. So here we get a beautiful picture that's copied from our paper. So the details of the MATLAB color graphics don't matter, but when I execute this, it's going to just show you this filter function for 32 poles. So isn't that beautiful? You can see essentially 0 out here, essentially 1 in the middle, and then this cage of poles. So a contour integral is doing things like that, a discretized contour integral. And you can see the paradox of contour integrals. They make an infinite error at the sample point. Isn't that crazy? Unlike interpolants, which are exact at the sample points, contour integrals make infinite errors there. But the benefit is they take a potentially huge problem living in the whole complex plane, and they restrict it to something small. That's what makes them fast, potentially. So when I do a contour integral, I'm multiplying my data by that. But now the next section is the one that tells you how people really do these things. Suppose instead of doing this expensive operation with 32 poles, I use a cheaper operation with fewer poles, like 8. But I apply it more times, like 4 times. So now instead of this function with n equals 32, I'll take this function with n equals 8 and its 4th power. What I'll get is a filter that's just as close to 0 far from the circle outside and just as close to 1 far from the circle inside, but its behavior near the circle will be sloppier somehow. But depending on your application, that may achieve what you want to achieve at smaller cost, because in large-scale linear algebra, if you can do backslashes at just 8 points, that may be a lot cheaper than backslashes at 32 points. And now this beautiful picture, I guess this one is going to produce a pair of pictures. So to remind you, oh, sorry, I've closed that one. Okay, here's the pair of pictures. So on the left, we simply have the filter with 8 poles, and the point is to be exponentially close to 0 out here. You can't really see that, but it's not that great. It's only got 8 poles. But when you take the 4th power of that filter, it's got still 8 poles, but they're quadruple poles, and it has just as good behavior out here as the 32-pole filter. So that's the picture that matches what people do in computational science. They use contour integrals intentionally in an approximate fashion to suppress certain components. And in particular, there are 2 schools who've been doing this. So one is a guy called Eric Polizzi at UMass Amherst, and he calls his method FEAST. And if you ask him why is it called FEAST, he says, I like that name. So he claims it's like Julia. You'll never get a straight answer. Why is it called Julia? I don't know. Anyway, he calls it FEAST. In fact, a couple of years before him in Japan, Tetsuya Sakurai had similar ideas, and both of them are starting from contour integrals in order to project huge matrix problems into a finite domain that they care about. It's interesting if you look at how they do it. They started from rather different points of view. For example, Polizzi was using Gauss quadrature rather than roots of unity and so on. But as the technology has advanced and become closer to science, I think that they're both finding the same methods are important. And in particular, it's crucial that they regard contour integrals not in the pure sense, but as filters which they can apply more than once. A key earlier person was Stefan Gödecker, who did similar things quite a bit earlier. And incredibly, having rushed very carefully, I reached an end, so I'm done.
Other questions, comments? Lizzie.
Hi. So a problem which comes up is that suppose you have 2 matrices, A and B, real symmetric matrices, and you look at the tensor A plus TB, then it's a well-known fact, also described in Carl Carter's book, that the eigenvalues of such a matrix will be real analytic functions. The eigenvectors will be real analytic functions, or similar. This is true even if 2 branches come together. So there's a singularity there. Nevertheless, they continue analytically through. So it would be, seems to me, a challenge to actually compute that numerically. Have you thought about that?
I haven't, no. I agree, that's very interesting. No comment. I do have a comment which is a little far-flung response to that. In this week's issue of Nature, there are 2 big papers about using non-Hermitian systems at the critical point where eigenvalues come together to make detectors that they claim are more sensitive than with Hermitian systems. So if anyone here is clever enough to read those papers and report to us about them, they might be pretty interesting.
Sorry. Along those lines, couldn't you read off quadratic coefficients, which would be more, quadratic coefficients instead of finding the roots themselves?
I don't understand.
So factorize the irreducible representation has quadratics and linear terms, right? So if you
Okay.
study so the case of where the real roots become complex, if you study the coefficients themselves,
Yeah.
that would look fine, even as
Yes. Well, I certainly agree that I have ignored the question of confluent roots and funny things that might happen. In principle, it wouldn't just be quadratic, it would be higher order too. But I,
you could use your polynomial
yes,
approximation
interesting.
way of
Yeah,
doing it.
yeah. I suppose you could, yeah. And presumably your point is that in real problems, often quadratic is special. That's the one that arises a lot, yeah.
Getting
Yes?
a formula which is rather like a barycentric interpolation formula. Is the whole theory generalized, so there are more such formulae in the complex plane?
Well, that's one of my long-term goals. You know, I'm a little old to have long-term goals, but that's basically my dream for the rest of my life, is to see this more deeply. If you want to join me. I believe there's a theory of hyperfunctions, which is a way of constructing generalized functions through the complex plane. It was invented by Sato in Japan and has sort of been buried by history because most of the world is full of real analysts rather than complex analysts. So everybody thinks distribution theory should be based on linear functionals. I think the beautiful approach is the complex plane, and so my vision for my next 20 years is numerical hyperfunctions and things just like what you're saying. Wow.
Practical comment on the square trap formula, which I love. Just a beautiful little formula. One of my students found trying out on the gamma function a little bit farther out that the errors actually became quite large. And this is because the implementation of the gamma function wasn't quite as good.
Oh, really?
For the
In MATLAB in particular? Yeah, that's interesting.
and so you can
But no, wait a minute. MATLAB's gamma function doesn't allow any complex. Talk about a bad implementation. Look at this. That's a bad implementation.
got somebody else's.
So at least MathWorks has quality control. If it ain't good, they don't include it.
But it can be surprising. It would actually work quite well for a small region. It wasn't until my student tried something well outside.
Really? That's interesting. Yeah.
And it was, you expect functions to have accurate imaginary parts. And that's,
Yes. Yeah. And it's amazing that they often do. Yeah.
Speaking of the square trap formula, is it a second derivative analog?
I don't know. I don't think I've heard of one, but yeah. Done.
Talking about the square trap. You use the analytic function is real on the real number.
Yes.
So somehow
Yeah.
this is a symmetry.
Yeah. And of course, most functions that we care about are, but in principle.
Clarify that point.
Oh, absolutely.
Come back later.
Oh, really? Good. Okay. Sorry.
With respect to root finding or zero finding of the function, if you use a parameter f, that formula, and all you know is the function is analytic, then a practical problem in terms of error estimate is that you don't know what else is staying outside. So in error estimates, that would be a huge problem. Whereas if you actually use the polynomial approximation way,
Yeah.
then you can rigorously justify everything.
Maybe that's true. I haven't paid close enough attention to be sure.
You don't know of any error estimates on the contour integral way of doing things.
Well, I think all of them at the first level give you the same result of O of capital.
But you don't know, suppose you don't know ahead of time
Yeah.
where the nearest zeros are outside
Yeah.
the contour, then you wouldn't have any way of finding error estimate.
That's right. No, I wouldn't know. Yeah.
Maybe two last questions before we move out from the photo. When you take a fourth power of dz and it's 8, is the polynomial analog to use like the Hermite interpolation?
Well, I don't know. I haven't thought about that. Maybe. Because certainly Hermite interpolation is analogs at high powers. Maybe. Yeah. Marco is our expert on that subject. Oh, Yuji. Hi. You arrived. Yeah.
Marcus, you said about scalarizing this resolvent that we probability 1, the poles are the eigenvalues of the matrix. Numerically speaking, it's not quite
Oh,
probability 1.
of course. Oh, you're absolutely right, of course. So for robustness, people do other things, often involving multiple vectors, you know, use a subspace version rather than a one-dimensional subspace, use more.
Is some theory known about the probability of small residuals?
I imagine everything's known. I mean, this gets into everyone's favorite subject these days. I mean, we're doing compressed sensing practically, right? There's a lot known. Yeah, but I haven't studied that.
The Murphy's law probability, that was probability 1 you'll have a 5.